and I'm super excited to be introducing this presentation on our vision for the future, which we are calling Space 2050. So we picked the year 2050 because it was far enough away to envision disruptive capability, but it's not so far away that it feels like science fiction. And so we do these exercises because in order to invent the future, we need to imagine it first. And so we've been performing an exercise over the last few years to come up with these ideas that point us towards the technology developments that we want to go. And science fiction is inspirational. It is important. We're boldly going. You know, I have the dream job that my 10-year-old self watching Captain Picard on Star Trek has, and I'm so excited. There's been a lot of twists and turns to get to this point in my career, but here I am. And for commercial civil space, I started in commercial communications satellites, rapid fast-paced programs for lots of commercial customers, and I've also worked on the Orion program and those missions for all of humanity. And so I'm so excited about Orion, NIRCam on James Webb, the InSight lander, all of these international missions moving humanity forward in science and exploration. And in my career, I've watched our concepts become reality. Right after the Orion's EFT-1 flight test, I was the Orion system architect, and we were finishing up the design for what is now Artemis 1 and 2. And I saw a lot of very, very pretty PowerPoint graphics in that time. But you know, last weekend, I saw Artemis 1 on the pad. And you know, of course, you know, I had to take a selfie with the rocket. And just standing there in front of reality on the launch pad, ready to go, remembering when it was just a vision, it was really inspirational for me and lots of other people. There were a lot of people down to watch the launch. But we are going, you know, starting now into that future, into a exciting, diverse future of all kinds of activity with lots of new technology, and this space community is what is going to make this vision a reality. So today we're going to talk about space infrastructure, expanding humanity sustainably beyond Earth. We're going to talk about some of the technologies that enable us to do that, things that might seem like science fiction, but we're working on it right now. We're going to talk about artificial intelligence being able to shrink to the design and analysis time on Earth. We're going to talk about robotic capability, where the robotics can make the decisions based upon the environment there. We're going to talk about revolutions in sensing and in communication, and how to achieve Earth independence with power and propellant on the moon. And then we'll finish by talking about all of that having impact here on Earth and applying that technology. So in we're also going to be taking questions. I'll come back at the end of the presentation and ask a couple of questions. So go to the Slido app and put your questions in there. That's how we'll take the questions, and we'll do that at the end. So let me introduce our presenters. So Eric Smith is the director of our Advanced Technology Center in Silicon Valley, who's responsible for artificial intelligence and data analytics and exploitation. And Sapna Rao is a system engineer that I work with in commercial civil space advanced programs. And also she's one of the organizers of the Space Generation Congress this year. So, and then we're going to get started here with a video. Let me go ahead and click that. Talking about our vision here at the moon.
Good morning, everyone, and welcome. Today I'm going to go over a number of mission scenarios that are set at some point in the future, 2050. And as Tim said, we picked 2050 because it's not so far into the future that it lives in the realm of science fiction, unbound by our current understanding of physics like intergalactic travel. But it is far enough out that we can rely on some revolutionary advances in known technologies to create major impacts on life here on Earth and in space. And we're going to create value at every step along the road. So as an example, and I'm not going to talk about this specifically in these charts, but as an example, if we were to pursue fully autonomous robotic surgery on the surface of Mars, even if we never achieve that ultimate goal, we would have major advances in technology for smart factories here on Earth and in-space manufacturing and assembly of large, complex structures in space. And in the same way, if we never achieve any of the goals, we will achieve some of these, but even if we never achieved any of the goals that we set forth in these scenarios, we're going to continue to deliver value at every step along the way. So we'll start with remote sensing. Remote sensing in 2050 is going to look very different than the remote sensing of today. And we'll start with this robot in the center of the chart. So I was having a discussion with a colleague yesterday about the inefficiencies associated with the historical process of design, manufacturing, integration, test, validation of complex systems, and the major improvements that have come about with model-based systems engineering. And what is model-based systems engineering today will become single-click design in the future. The robot in the middle of this chart is building a satellite in response to a demand from a user on the ground who wants to add capability to this constellation. I need EO imaging type 1, click. Or demand from the constellation itself as a result of having lost one of the assets, click. It's a complex series of actions in response to a single need statement. These satellites don't have solar arrays. They're getting power from an internally contained nuclear source, or they're getting it beamed from a central power repository somewhere. These satellites have hexagonal body shapes so that portions of the constellation can be reconfigured to perform specialized mission functions. And although it looks like these things are doing imaging, there's no telescope. These items, there are no telescopes on these payloads. They're doing interferometric imaging directly at the entrance pupil of the system. In 2050, with low cost to no cost to orbit, single-click design, fast communication systems, and AI and high-performance computing at the edge contained on every one of these nodes, constellations like this will be able to track every object on the face of the Earth persistently. Every object on the face of the Earth persistently. And initially that sounds a little scary, a little Skynet-y. But imagine the impact on disaster relief. Real-time automated damage assessment anywhere on Earth in the case of fire, flood, earthquake. Automated ingress, egress, path planning for ground and sea vehicles. And as quickly as humans can operate and think about disaster response, these systems can go much, much faster. Smart factories, automated ground, sea, and air vehicles and first responders will work together to bring the right relief to these remote locations in the fastest time possible. So I talked in that last chart about satellites doing interferometric imaging at the pupil. This is the segmented photonic imaging detector for EO reconnaissance, or SPIDER. SPIDER replaces the optics in a system that do that complex transformation of phase and amplitude at the pupil to form an image, and it just operates at the pupil directly. So we've taken a operationally simple system, that optical system, operationally pretty simple, and replaced it with this seemingly very complicated one. Why would we do that? What do we gain? Well, for starters, we gain 1 to 2 orders of magnitude reduction in size and mass of the system. Big cost drivers, of course. But we've also replaced that very time-consuming process of the design and manufacture of these exquisite optical elements whose surfaces have to be figured to within a handful of microns. And the optical systems, or the optomechanical systems that have to deliver these optics to orbit to within a handful of microns of their intended design locations. SPIDER does the imaging and the alignment computationally. So this is something that we've demonstrated, of course, in simulation. We've demonstrated the critical technology components in the lab, and we're working with NASA to launch an early version of SPIDER for solar imaging and for Earth imaging. So this is a technology that is becoming real. Not every system, of course, is going to look like SPIDER. We're going to rely on conventional optical systems, for example, to build very large aperture telescopes that will one day image a single planet around another star. But line of sight pointing in these large systems is very challenging, very challenging. And so why are they so big in the first place? So, well, of course, there's the light collecting aspect of it. We're trying to see a very tiny, faint thing a long way away. It doesn't reflect much light. So we've got to collect a lot of photons. But then there's the resolution aspect of it. We think about the resolution power of these telescopes as kind of being lambda over d. Lambda being the wavelength of light that we're using to image the planet, and d being the diameter of the telescope. That's a very tiny angle. And in order not to spoil the resolution of that exquisite system, we have to maintain the pointing to within a small fraction of lambda over d during the entire integration time, which, again, can be quite long because we're trying to image a very faint object. Lockheed Martin's solution to this is kind of pictured in this graphic on the left. So this graphic shows a telescope or an instrument on the front end, and on the back end is the bus. And inside that little gap between the two lives an innovation called disturbance-free payload. Disturbance-free payload is a 6 degree of freedom, non-contact, active line-of-sight maintenance system that both points that front-end telescope and isolates it from the exported forces and torques in the bus that would otherwise spoil that line-of-sight stability. Now, if in the future we build systems that transmit data and power wirelessly, then we really have no mechanical means by which disturbances in the bus can ruin the resolution of these exquisite instruments in the front end. So line of sight is one way that this can get ruined. The other way is large optics tend to be a little bit floppy. And I'm talking floppy in the optical sense, a few microns. A few microns motion of that large primary structure is enough to completely ruin the resolving power of the telescope. On the right-hand side, we show a graphic. On the upper graphic right-hand side is a simulation of that primary mirror bending caused by disturbances from the bus. And on the lower right-hand side is the same disturbance with disturbance-free payload. And we get about 1 to 3 orders of magnitude improvement using that technology. So that's simulation. We've actually built this in the lab, and in fact, the graphic on the left is an image of a lab demonstrator that we've hung from the roof with fibers and demonstrated more than 60 dB of isolation. So let's go to communications. Of course, every space asset is going to need communications. And in 2050, the density is going to increase exponentially, density of objects in space. Not only the number, but the amount of data that they ingest. They're not only going to collect the data, but they're going to share the data and information about that data with other members of the constellation in addition to the ground stations. And that's going to require extremely fast, secure, resilient, dynamic, and intelligent communications. The resilient piece we think of as being achieved through essentially numbers, as we have pictured here, large constellations interconnected with an optical mesh network, redundant comm links, covering the Earth for global coverage, thousands and thousands of these communication nodes, so that if we lose 1 or 2 or 10, the degradation in capability is gradual. Particularly if we have AI living on each of these nodes that can dynamically change the network topology to respond to the changing need. The need for these high-speed communications, of course, extends beyond just Earth or LEO or GEO. It goes to the lunar surface, to the cislunar space, and all of the points along that Earth to Moon journey. By 2050, we expect a persistent human presence on the Moon of hundreds of astronauts per year that are dispersed among fixed and mobile habitats. And in order to prepare for that reality, Lockheed is building the Parsec service. The Parsec uses a system of small satellites that work in unison to provide continuous communications and navigation from the Earth to humans and assets that are either on the surface of the Moon or on their way there. And the foundational technologies upon which Parsec are built are already in existence. The bus is the deep space smallsat bus being built for Janus and the Lunar Trailblazer. We have what we call the SmartSat framework that allows on-orbit reconfigurability for mission flexibility. Our Compass and Horizon products provide autonomous mission planning and command and control. And finally, we have a Hivestar mesh network that enables automated task distribution around the constellation with no human intervention. And the first Parsec node is scheduled to be delivered in 2024. So we're building this infrastructure for 2050 starting today. Let's see. I failed to mention in that communications chart the secure piece. When we think about, or when I think about secure communications, as you do, you probably think about quantum key distribution. And a lot of organizations around the world, including Lockheed Martin, have demonstrated successfully free space QKD. And the problem there has historically been the bandwidth. So I said these systems have to be fast, secure, reliable, dynamic, and intelligent. And if we choose QKD, which is a very secure form of communication, we're going to, or we thought we were going to, compromise on the fast piece of this. I'm very excited about the work that Lockheed Martin is doing in the area of quantum comms. We have leveraged 3 key innovations to solve the fast piece of the communications need while simultaneously solving the secure. So innovation number 1 is how many bits of information can we stick in that photon? So photons are quantum objects. They're not just on or off. They have all kinds of quantum numbers that we can exploit. One of those is angular momentum. So the team is they're multiplexing photons in order to pack more bits per photon, multiplexing in quantum number, multiplexing in time, and multiplexing in space. So what's shown on the board here, this helical beam, these are vortex beams of photons with different quantum numbers, or different angular momentum quantum numbers. In the middle, we have a thin film phase plate that's used to create spatial multiplexing. And in the center is a picture of an APD, Geiger mode APD array that can detect the single photons in their multiplex states. So those 3 items give us more bits per photon. Second innovation that's being leveraged is superadditivity. So superadditivity means we can operate these systems in any conditions. We don't have to just operate free space QKD at nighttime. We can deal with much higher background levels with superadditivity so they can be operated 24/7. And the third is the use of high-rate non-classical sources that have been enabled by years and years of investment from the US government and near-perfect waveguides. This system has been demonstrated in the lab. We're currently running a number of experiments outdoor, all going very well, and we expect that within 2 years, we'll be doing our demonstration of this technology, scalable in bandwidth, on orbit, to solve the secure piece of the communications puzzle while not only maintaining the bandwidth, but increasing by what we think is an order of magnitude. Electronics for space. Boy, that's always been a tough one. We often hear criticism that space is using electronics and processing technology that's years behind the state of the art. And so how in the world are we going to achieve this future reality with AI and autonomy at every node in space if the electronics are so far behind the state of the art? One of the approaches that we're going to take is the development of carbon nanotube electronics. So why? Why carbon nanotubes? Well, one, they're inherently radiation hard. I mean, that in itself is huge. They don't suffer the radiation sensitivity that silicon-based electronics have. Inherently radiation hard. Number 2, they're very low power and non-volatile. And number 3, they're stackable. It's simple to construct 3D structures of carbon nanotube-based circuits to make very dense, very small packages. And you don't have the heat associated with the stacks of silicon because, again, they're very low power. The memory we've created and flown carbon nanotube-based memory called NRAM. Flown that, check. Memory, check. We've created field effect transistors in the lab that demonstrate electron mobilities comparable to those in silicon. So we've got the transistors, check. So with the memory and the transistors, we can start thinking about building these systems on chip, 3D stacks of carbon nanotube electronics. Now, of course, we're still going to rely on standard approaches for putting electronics in space, of better shielding techniques. I mean, when we get to the moon, we're probably going to just bury large installations of electronics because that's a very effective way to shield them. Stick them under the ground, they're shielded, running just fine. But we think carbon nanotube technology is going to be an important piece of that puzzle. There are a lot of environments that we just don't understand very well in deep space, but we need to go there and explore. So let's take the recent rendezvous of Osiris-Rex with the asteroid Bennu. Very successful mission, and Lockheed Martin is very proud of its contribution to that mission and its success. But the surface of that asteroid was very different than what we had expected. So when we got there, we have the sample collection arm that's going to reach out and grab some, the content of the surface. And when we got there, that arm sank 2 feet under the surface of the asteroid. It was way softer than we had ever imagined. And it was fine. The control system on the free flyer had enough phase and gain margin that it was able to pull back from the asteroid, and it was, again, a great success. Now, had we landed on the surface of Bennu, the outcome may have been very different. And so we need to build probes that have the ability to reason about their environment so that they can make smart decisions, intelligent decisions without human intervention. That's where Carl comes in. Carl is causal and reinforcement learning. This is a reinforcement learning tool that's being developed by Lockheed Martin and JPL. And it goes beyond the reinforcement learning, which takes action and gets good or bad rewards from the environment. Carl seeks to understand the causal nature of the environment, to understand the root cause of a good or bad reward, so it can make intelligent, good decisions in the future without having to first make bad ones to understand how to get better rewards, when the environment changes. And that's going to be important when we send probes to areas where human interaction just isn't feasible, like a probe that's going to look for life under those icy sheets on the surface of Europa. So I've talked a lot about technology development, and I'm going to hand it over to Sapna, who's going to talk about how some of this technology might lead to a permanent human presence or a persistent human presence on the moon and enable Mars. Sapna.
Awesome. Thanks, Eric. So now I'm going to talk about our future vision for Space 2050. And I'll grab the clicker from you so I can do that. Thank you. So first off, we see 2050 as being Earth independent. So we're able to do everything we want to do on the moon with the resources from the moon. And this will really enable sustainable lunar exploration. So what is Earth independence? That is really getting all the resources you need for different functionality and infrastructure on the moon right there with you. So that kind of comes in 2 flavors. One being propellant, which we can get using lunar in-situ resource utilization by taking that icy lunar regolith that's at the poles, converting it into water, and then taking that and making propellant and storing it in propellant depots. Now, although in 2050 we expect to decrease the cost of launch, just having those resources available on the moon, ready to go, is really going to jumpstart us to Mars. So that is a very key resource to have available. Other than propellant, we now have power. So we want to have a diverse portfolio of power sources. So we are planning on leveraging solar array power and also fission surface power. Having these two types of power sources is going to allow us to have constant power available and allow us to power our infrastructure no matter when in the day it is on the moon. Now, these two resources are really going to be part of the key infrastructure for the moon and allow the crew to really just concentrate on science and exploration and not have to worry about figuring out what they're going to do. So in addition to those two resources, we have mobility, which is a key function for completing all your scientific exploration and objectives on the moon. So Lockheed Martin has its lunar mobility vehicle, which is a partnership between Lockheed Martin, General Motors, MDA, and Goodyear. So working with all these companies, we are providing this service of mobility all across the lunar surface. And the really neat thing about this vehicle is that it comes in kind of two formats in one configuration. So you can have a crewed option, or you could have an uncrewed option. So you can operate it autonomously and actually not even need people to work it. So what this really does, it enables us to have our lunar infrastructure be built even though crew isn't ready to be on the moon yet. So we can set up the infrastructure and also pre-position resources. So maybe have a lunar mobility vehicle go to the next landing location of astronauts, ready to take them to their habitats. So having that capability is really going to let astronauts access the whole lunar surface. And additional to mobility, kind of in the same vein, is having access to power wherever you are on the moon. And we plan to do this with power beaming and having a distributed power network. So using our diverse portfolio of power sources, we can now power any lunar infrastructure wherever it is on the moon. We can power it with power beaming. And we are doing this now with Athena. And I'll actually have Eric, because you work on it, talk a little bit about it.
Yeah, so Athena is a system that we use to understand and solve all of the engineering challenges associated with getting a large amount of power from point A to point B. Now, Athena, the goal here was directed energy. We're talking about defense against things like UAVs, quadcopters, mortars. I mean, we took out mortars with this thing. And what we learned with Athena was how to take these very robust and scalable sources called fiber lasers and build a system that will spectrally combine these fiber lasers so that we can take small frequency differences between a whole bunch of lasers and have them exit the system as a single high-power beam. Athena was a trailer-sized demonstrator. Very successful, but trailer-sized. What's pictured on the right-hand side of this chart is LLD. This is essentially a productized version, much more powerful, much more mobile. And we, having worked on a whole lot of space missions at Lockheed Martin, understand how to make LLD operate in space as a power beaming source. All right. Thank you, Sapna.
Awesome. Thanks, Eric. And the other cool thing about having this capability of power beaming and constant power sources available is we can do power as a service. So all the other countries that are going to be on the lunar surface and all the different companies as well, we have power as a service, and we're going to be able to provide that to everybody on the lunar surface. So now we've talked about all these really awesome lunar technologies, and they're really getting us to Mars. They are really helping us transit to Mars. And here we have Lockheed Martin's Mars Base Camp concept, and it is a new version with nuclear thermal propulsion. And now we've had lessons learned from fission surface power on the lunar surface. We've done it, we've experienced the challenges of nuclear, and now we're taking those lessons and getting us to Mars with NTP. And NTP really is really going to be super important for really improving how we do this with its high thrust and high efficiency capabilities, and just being able to do it in a better way than chemical propulsion, which would work, but this is going to do it in a more efficient way. In addition to being highly efficient and having high thrust, it also can cut off a few months of transit time and really enable aborts, enable some abort capabilities as well. So NTP is a huge powerful technology that we are excited to start working on and get that on the way to Mars. In addition to NTP, we also have our reusable lander. And those propellant depots that we saw on the lunar surface, we're now taking those with us on our Mars base camp, and we're going to be able to refuel ourselves in orbit, leveraging that lunar propellant that we just made. So it's really, again, that Earth independence that is key for our future vision is coming back. We don't need to go back to Earth and get propellant. We have it from the moon because we've made it. So really, reusable landers also allow you to go wherever you want on the Martian surface. You can access all locations. You have way more improved scientific exploration opportunities, and having that be refueled in orbit is very important for the future vision. And after we've transited to Mars, now we're going to go on the Martian surface. And this is where everything really comes together. So we have all the technologies that we did on the moon, and now they're all coming together on the Martian surface. So we have, again, propellant depots, we have various power sources as well, and now we are ready to explore the whole Martian surface, and we have it all learned from the moon. So really, our future vision for 2050 is going to the moon, advancing what we're doing there, and taking it to Mars, and having sustained presence on the Martian surface. And now I'll pass it back to Eric to bring us back down to Earth.
All right. Thank you, Sapna. Pictured on the chart is an example of individual component technologies that will exist in the smart and connected cities of Space 2050. Smart factories, environmental monitoring and control, level 5 autonomy for humans and cargo. But I want to talk about a scenario that for me really exemplifies the power of the connected and smart city in 2050. So in about the 2015 timeframe, there was an accident in a city north of San Francisco. There was a man in a truck, pickup truck, had a heart attack, lost control of his vehicle. The vehicle left the roadway, it became airborne, and crashed into a car parked in a restaurant parking lot. And I do not know the fate of the man driving the vehicle, but I do know that miraculously no one else was injured in this incident. And in that moment, when that man had that medical event, he was isolated and alone, helpless. In 2050, this is how that scenario would play out. So a man is a passenger in his L5 autonomous vehicle, and his wearables detect the early signs of the onset of a cardiac event. The car plans a path, knowing the inevitable, plans a path to the nearest ER. It talks to the staff at the hospital who assemble a team in the ER prepared to receive this patient. The hospital's inventory system realizes that it's missing a critical piece of supply that it normally has on hand but just doesn't, and calls for an autonomous drone delivery of that supply. Meanwhile, the vehicle tells all the other vehicles and the traffic lights to clear a path to save critical minutes in transporting this man to the ER. So in 2050, with the smart city, we will have every device able to talk to every other device and do so for the betterment of humans. On my first chart, I talked about the scenario of persistent surveillance of the surface of the planet and its impact on disaster relief. And while we aren't doing that at that scale today, Lockheed Martin is making investments to make real impacts to disaster relief today. So we've invested internal research and development dollars on AI tools that are connectable in a Lego block fashion, that do classification, fusion, reasoning, prediction, and decision making. And we've partnered with NVIDIA to leverage their hardware and data visualization expertise. And we've built the command and control and data pipelines to develop what we call firefighting intelligence as a service. Firefighting intelligence as a service takes observations from multiple domains, including space, and considers the conditions on the ground. Where is the fire front currently? What are the fire loads in the area? Where are the critical infrastructures? What is the topology of the land, etc.? And presents a predicted future state of that fire line, should we take or not take certain actions, and presents that data to the fire chiefs on the ground so that they can make smarter decisions or help them make decisions about the best use of their assets, their critical, precious assets in the attempt to minimize the impact of this fire. So, in summary, 2050 is not surprisingly about missions that can be realized through revolutionary advances in autonomy, communication, computing, and artificial intelligence. And I'm really excited to be part of this worldwide community that's working so hard to accelerate that revolution. Thank you all for your time.
All right, thanks, Eric. Thanks, Tapna. So everyone, please go ask questions. I got the iPad up here to take a look. And I've got a couple of my own as we wait for the audience questions to come in. So Sapna.
Maybe we could put the QR code back up.
It's up.
Oh, okay, good.
Thank you. So Sapna, you're working as a system engineer right now today on a lot of stuff that you're talking about. What are you most excited about that you're working on?
So I'm working on the cryogenic demonstration mission, which is a NASA tipping point. So what that really is it's advancing the technology readiness level of cryo storage. And we talked a lot about cryo-based technologies today, and really nailing down storing it with reducing boil-off and making sure we have a lot of cryo available. Having that technology nailed down is so critical, and that is what I'm personally most excited about. One more small thing is I also am really interested in AI, and we're working on using lightning to detect or predict wildfires. And in Colorado, where I'm from, there are very bad wildfires, and I'm sure a lot of you have also come from places with wildfires. And actually about 40% of wildfires are caused by lightning strikes, which is a crazy statistic. So by using machine learning and AI and the lightning data we get from Lockheed Martin's global lightning mapper, we're able to figure out where those are and help inform first responders to save lives and save forests. So those are my two most exciting projects that I'm working on.
Thanks. So Eric, a question for you, and this is around security. So if cars have access to our health in real time, how do we address those security issues having that private information?
I mean, security issues in the future are going to be it's the same set of security concerns that we have today, really, in our, how do we protect our genetic information when we, out of curiosity, offer up our entire genetic makeup to a company that does things with it that, frankly, most of us are probably not completely aware of. So I think the first piece in achieving that future where we have our medical data and other sensitive information shared with other entities is to educate the public on how this data is used, why it's used, what are the real pitfalls and risks. There are real concerns that have to be addressed with that kind of personal information, and there are imagined threats that are in people's minds because they don't really understand the real nature of that data exchange. And I think the biggest threat to the future is that imagined threat in the mind of the public that will put a stop, an immediate stop to that kind of progress because they're afraid of what's going to happen. Public education, I think, is number one.
All right. Thanks, Eric. So, Sapna, in terms of power, NASA's talking about having a lunar power grid where companies and agencies and other actors can provide power, draw power. What's Lockheed Martin's take on that?
So I think that surviving the lunar night is really difficult. And if you have the infrastructure in place for that, you're going to be able to do a lot more exploration. So having this distributed power network and power as a service available for everyone is going to allow universities and different countries who might not be able to tackle that really difficult problem with the resources they have, they'll be able to purchase that as a service, and it will really enable them to do a lot more. And feel free to add anything else to that, Tim.
No, that's great. So looking at the questions here, I think there's one that I'm going to take, which is, how are we working with relevant regulatory agencies to get nuclear reactors launched? And so certainly the regulatory aspects of that is just as important as the technical and the business part of space nuclear. So we're working carefully with the agencies along with our customers who, as part of the government, are able to interact. So it's really a team effort to understand all of the safety issues with nuclear reactors, work through those and have them be perfectly safe. And the nice thing about when we talk about a nuclear fission reactor, we don't activate it until it's into space. And so that really is a key part of making that safe. All right, let's see. So, and maybe for both of you, beyond the Earth, Moon, and Mars, what scientific missions to the outer solar system would you love to see by 2050?
Oh, okay, well, beyond Earth, Moon, and Mars, my favorite mission of all time is absolutely Europa. I'm completely obsessed with what might be happening in that liquid ocean underneath those icy crusts. I'm going to work like mad during my lifetime to set up a successful mission to look for life on Europa.
So mine is actually going to happen soon. It's going to Venus, and Lockheed Martin is going to be launching 2 spacecraft missions to Venus in I think around the late 2020s-ish. So Venus is we need to learn a lot from it because one, it's actually pretty close to us, and it could be really similar to what happens to our Earth in the future. And just going to Venus itself is going to be very, very difficult. So I think the technological innovations that we will have along the way will just greatly be a huge advancement.
All right. I think we're running out of time. So thank you, everyone, for coming and having us share our vision here. I'm really excited about the future and what this space community is going to do to really invent that future of 2050 for all. So thank you.